I'm Rob Bowling, and I'm going to present proof 4.2, which basically says that if for a continuous a function is continuous if and only if for every sequence xi converging to xi, the limit of xi as I goes to infinity equals, or the limit of f xi as I approaches infinity equals f x i. And we can prove that, and since there is an if and an only if part to the proof, we'll have to do two steps in showing that this proof is true. So first I'll start with the only if part of the proof, and thereby I'll be assuming that f is continuous at x dot. And we know that if f is continuous at x dot, we can write that for every delta greater than x dot, absolute value of x dot minus x, that implies f x dot minus f xi is less than epsilon for all epsilon, and that should be there existed delta. So now we'll take a sequence xi, and our goal now is to choose an n such that for all lowercase n greater than uppercase n, xn minus x dot is less than delta. This shows that the function converges, so we have to find, and we're guaranteed by the continuity of this function that such an n exists, or well, such a big n exists. I'll write that. And since we know that xn minus x dot is less than delta, because we have a continuous function, we can write fxn minus fx dot less than epsilon. And this proves that for a continuous function, all sequences are good and this shows that for a continuous function, a function is continuous only if all sequences are good sequences, and by good sequence I mean that for a sequence that converges, the limit of xi as I approaches infinity equals f x dot, and x dot is the value to which the sequence converges. And now I'll prove the if part of that proof, but I'll do that by proving the contrapositive. So the proof is f is continuous at x dot if and only if for every sequence xi converging to x dot, the limit as I approaches infinity f xi equals f x dot. So I'm going to do the contrapositive, and I'm going to assume the negation of part 2, or the negation of part 1, and part 1 being the continuity. So I'm going to give myself a discontinuous function, and from a discontinuous function I can write for delta greater than x dot minus x, that implies fx dot minus fx is greater than epsilon. And so in constructing a sequence, I'll take a sequence xi, and I'm going to make my delta value 1 over I. And I know by the principle, because this function is discontinuous, I can find 1 delta such that xi minus x dot is less than delta. But because this function is discontinuous, I can show that f xi minus fx is greater than epsilon. So I know for this sequence, the sequence will be discontinuous at that this sequence is I'm basically showing that this is a bad sequence. But now I'll show that this sequence also converges to x dot. So we'll show that for all n, or no, there exists an n such that for all n, 1 over n, because I defined delta to be 1 over I, and we're treating n as one to be a subscript of x, such as xi applies to xn, or n can be basically be substituted for I. So 1 over n is greater than xn minus xi. And this shows that the sequence converges to xi. So by negation, I showed that for a discontinuous function implies all sequences are bad sequences, and that the sequence converges, but there's a discontinuity value. And by doing so, I've proven that, because I proved that the negation was true, I've thereby proven that the original if statement was true, which is that if for every function xi converging to xi, f is continuous. I proved that by using the negation, and thereby I proved proof 4.2. F is continuous at xi if and only if for every sequence xi converging to xi, limit of I as I approaches infinity, f of xi equals f of xi. Get that?